Yes, here. DFA to regular expression. RE means regular expression via state elimination. Normally we need to eliminate a state from a DFA. It always compel us to do like this because most often one may say that these are the requirements to create a regular expression from a DFA. So what does it mean? Starting with an intermediate states and or with intermediate states and then moving to accepting states. Apply the state elimination process to produce an equivalent automation with regular expression label on the edges. Okay, so we will start from intermediate states and then we will move on to the accepting states. I have already taught accepting states and intermediate states before, but I will repeat them again. But on the next slides, let me teach you the simple method of how to eliminate the intermediate states here on this slide. So we then you one needs to apply the state elimination process to produce an equivalent automation with regular expression. Okay, regular expression labels on the edges. Okay, so what does it mean that we will have to move to the accepting states of the DFA so that we can apply the elimination process to produce the equivalent automation. I mean, equivalent automation means the machine or the DFA which we were having before the elimination process and the DFA which normally we get after the elimination process. So both of the DFA are always equal, but why we remove or eliminate the intermediate states? In order to reduce the cost, reduce the complexity, to make the machine simple, and further it will perform both of the DFA will perform the same task. So with regular expression labels on the edges, I mean expression labels on the edges, what does it mean? That on the edges in the DFA we normally put the expression labels, and at the end we collect all those labels in order to get the regular expression in full form. Okay, I hope you are understanding what I'm saying. Guys, sometimes I will switch to other local languages as well, like Urdu, which is the national language of Pakistan, and another language, Pashto, which is normally is being spoken in the north of Pakistan, because we are having students from different areas, region-wise. So we will help all of them to understand our lectures. Some of them are very good at speaking and understanding English, and some of them sometimes they struggle with English. So that's why it will be my compulsion to move to different languages sometime. Okay, but though often I will try my best to. Most often my lectures will be in English. Okay. So the result will be a 1 or 2 state automation with a start state and accepting state. What does this mean? That in the machine, in the DFA, we'll be having a start state and we'll be having an accepting state, and in the process we may have 1 or 2 state automation machine or DFA, or we may have more than 2 states, and we may eliminate 1 or 2 states as well in order to make our machine, our DFA, more simple and also to reduce the cost. Okay, let's move onward. So this is what DFA to regular expression state elimination, how we normally eliminate the states. Okay, so if the 2 states are different, we will have an automation that look like the following. Yes, in this DFA we have an automation. This is start, and here we have R, and then we have another state U, and then this is the H. So what happens at when we reach to the start to the first state? So here the machine, you may call it it repeats itself, and then it also we may sometime need to move on to the next state, and then from the next state you may come back to the R state, and then you may go again to the next state, and then it may repeat itself it's not good to call it its self loop or cycle here, as we are studying DFA to and NFA or compiler construction. But this is what this edge means, that while reaching on this state, it may visit itself again. Most often in many machines, in many DFA, it happens. One of its very good example is ATM machine. In ATM machine, normally checking the balance, going back and then coming to check the balance. There are a lot of transactions and routine process which we normally operate, or which we normally do in our usual life. So this is our DFA diagram, and DFA stands for deterministic finite automata. What is our job here? To convert this DFA to regular expression, and here is the regular expression. You can see, and this is what we derived from this DFA. So we can describe this automation as, we can in other words, these both are equal, this DFA and this regular expression. You know, R plus S U and static T are multiplication T, then brackets, then closure. I mean, you know, in compiler construction, plus means one or more and static means zero or more. Okay, so static SU and then static. So if somebody asks you, are these two equivalent? I mean, this regular expression and then DFA, so you can say yes, they both are equal. This is another form of this DFA, and this DFA is the diagrammatic, you may call it a form of machine normally developed for this regular expression. Okay, so let's go ahead. We will study how to remove the state. Okay, but before going to the next slide, I would like to go to the comment section in order to read the comments from students so that I can answer them before moving further. Okay, normally I receive normally I'm posting currently this I'm on in two live session. The first live session, it is on Facebook, where normally students are listening my lecture in a live form, and they are putting comments in the comment section. And the other thing is competition. I'm also recording this video on my screen so that later on I can upload this video to my YouTube channel. Okay, so let's go back to the Facebook first in order to read the comments from students. Okay, I have some students here and they are putting hi, hello, and they are also saying assalamu alaikum, wa alaikum salam. So sir, second, okay, they are also putting their attendance. So normally simple attendance, no questions so far. So let's go back to our lecture. And okay, the recording is also in progress. Okay, so let's go. Okay, so as I taught you this slide, okay, next DFA to regular expression state elimination. Okay, 3. You know, we have this is 3, this is 2, and this is 1. So 1, today I taught, I took a start from this slide, then 2, and then now 3. On 3, I eliminated this, you know, this second state, this U state. In this slide, I eliminated. I just try to restrict myself to the first state. Why? Because we are learning, or we are learning how to eliminate states. Okay, so this is state elimination. If the start state is also an accepting state, then we must also perform a state elimination from the original automation. That's get rid of every state but the start state. This leaves the following. Okay, you know, this is the starting state, and it is also the accepting state. You know, this is the accepting state. It is also accepting. Here is the H. So what I did, I separated this starting and accepting states from the final state. You can see here is the final state. It's not good to call it final state, but the next state. Okay, so here, and R static is the regular expression equivalent for this DFA. We can describe this automation as simply R static. So R static is the equivalent automation for this diagram. And why we are studying this? Because in compiler construction, or even in these days in high level languages, DFA, NFA, regular expression, these kind of concepts are applied a lot of times while developing compilers, assemblers, interpreters. And when you click on compile, so what happens at the back, such kind of NFA, DFA, these kind of particularly regular expressions, these kind of things runs to accomplish your objectives. And DFA and NFA, in other words, you may also develop machines for this kind of diagrams, NFA and DFA. And why we normally apply the state elimination process, so that we can get simple machines with less complexity and with less cost. If you are having unnecessary states in your machine, so it will cost you a lot. Okay, I hope you are understanding what I'm saying. Let's move to the next slide. DFA to regular expression state elimination 4. You can see 4 here. If there are n accepting states, I'm repeating, if there are n accepting states, we must repeat the above steps. The above step means steps on last slides, last 2 or 3 slides. Okay, so we must repeat the above steps for each accepting state to get n different regular expressions. Okay, I hope you are understanding. Repeating again, I'm repeating again, if there are n accepting states, let's suppose we have n accepting states, we must repeat the above steps for each accepting state to get in different. Yes, if we are having n accepting states, so each time we may apply the state elimination process, and each time for different paths, for different edges, we will get different regular expression. And as there are n accepting states, so we will receive we will get n regular expression from R1, R2, and it continues until it reaches R with a subscript n. It means regular expression n. So for each repeat, we turn any other accepting states to non-accepting. Yes, for each repeat, what we will do normally, we turn any other accepting state to non-accepting. Okay, we will make it non-accepting for the first. I mean, at each repeat, at each run, we will take one state as accepting, and we will consider other states non-accepting in order to reach our goal. So the desired regular expression for the automation is then the union of each of the n regular expression. Okay, what will be the desired regular expression? The desired regular expression will be the union of all the regular expression then that normally we get. Okay, I hope you are understanding. Let's move to the next slide. Here another example, DFA to regular expression example. So convert the following to a regular expression. Okay, we have a DFA, and our job is to convert this DFA to a regular expression. So first of all, what we will do, first convert the edges to regular expression. So what we do, we will convert these edges to regular expression. Okay, so here I have written the diagram as it is, and the converting process will start on the next slide. Okay, let's go to the next slide. Here DFA to RE means regular expression, and DFA, you may call it a machine, or you may call it automata. Deterministic finite automata. Okay, DFA. So this is our first slide. I forgot to put one here because we started the example from here, and this is our next slide. Okay, 2 is here. I have put the 2 as this is the second slide of this example we are currently studying. So eliminate state 1. What I will do, I will eliminate this state 1, and yes, here I eliminated it in the diagram given at the bottom of the slide, or down given below this first diagram. Okay, so here no state 1, it has been eliminated, and here we have state 1. So then note edges, note edge from 3 to 3. Yeah, from 3 to 3. This is a start state. At the same time, it is also an accepting state. So what I did, I considered state 1 as a non-accepting state. So, and zero for this edge, and then 10, 1 and 0, 1 and 0. This is an edge 1 and this is 0, edge coming from 1 to state 3, state 1 to state 3. So for this 1 and 0, I wrote it like this: 0 plus. Why plus? Because it is in the extension. Okay, 0 for this edge, then 1 and 0, and we normally write it plus 0 plus 1 0, and then this one and this one, 1 1. Okay, 1 1. So for these two edges I wrote 1 1 here. This 0 plus 1, it came as it is on its place. So here down is the regular expression. Okay, so the answer is 0 plus 1 0 and then static. So for this 0 plus 1 0, I have put the static as it is repeating. I mean, it is accepting again and again. So one may visit or one may come to the state 3 again and again. And then 1 1, here is the 1, okay. And then 0 plus 1 y in the bracket, and y static, because 0 plus, it is also repeating, it is also accepting and again and again. If one will come here to state 2, then he or she may reach again on state 2 again and again. So for again and again we normally put static. Okay, and 1 1, no static on 1 1, because it will be traversed one time while going towards state 2. Okay, and y static on 0 plus 1, because here again accepting state, again it may come on this state again and again. Okay, so here is the answer. Okay, this is the regular expression for these DFA. I hope you are understanding and you are with me. Let's go to the next slide. Second example, we got another example. I hope you will understand this example easily. Automata that accepts even number of 1. This is an automata for what? For accepting even number of 1. If the input which will be given to this machine, to DFA, so it will only accept even number of ones. Okay, how here start, we normally take a start here, and this is the state 1, and it is also an accepting state. Okay, it may repeat itself, one may come again and again to this state. This is what it means. And then 1 next edge, then you may go to the next state, and then it is also an accepting state, and it can also visit itself again and again. So the label for this edge is 0, you may call it the bit. Okay, sometimes we also call it literal. Anyway, so then the next edge is 1, the edge level is 1, and it is going to state 3, and state 3 is again in accepting state, so there is 0, and then from state 3 you can come back to state 2, and then you can go to state 3, or it can revisit itself again. I mean, it is an accepting state. So what will be the regular expression for this DFA? This is now our job. Okay, let's start the eliminating process. Eliminate state 2. So we will eliminate state 2. So we will eliminate state 2. So how this label will become? You see, 1, then 0, 1 0, and then static 1. Why static on 1 0? Because this 1 and 0, this 0, it is an accepting state, so it may be repeated again and again, so there must be static on 0. And 1, this is 1 time, this is not this has not been repeated again and again, so no static on 1. And then after static again 1. Okay, 1 time visit, and then 0 again. You see, so here 1 on and 0. Okay, this is, let me start again. 0 as it is, 1 and then 0, and then static on 0. You understand this? Then 1, and then from 1 it can come here, it is 0. So it is an accepting and then after 3, where it can go? It can go to 2. So 1. After that, yes, we are adding 1, and then it can go to 0. Yes, here is the 0, and it may repeat itself again and again. So there is a static, and after this again it can go to state 3. So here is 1. So after static it is 1. Okay, it is 1. Okay, so after static it is again 1. I hope you are understanding what I'm saying. You have understood this. Okay, so let's go to the next slide. Okay, second example. Okay, uh, uh, so I think yes, here is the regular expression. You see, the answer is regular expression for this diagram. I forgot to tell you. So here is the regular expression for this example. So this example finished. Let's start another example. Automata that accepts even number of ones. This is also an automata. This is what I taught to you. And here on the next slide, here this is just 0 static. This one is 0 static, and then can ignore going to state 3. Okay, we can ignore since we would die. Yes, we here we can die because the machine may halt. I'm using the word halt. It will always repeat itself again and again and again because there is no any other state to get out of this place. It will always accept, and this process will keep continue until a time will come when we will die here on this state. So two accepting states. This is also an accepting state. This is also an accepting state. Okay, turn off state 3 first. We need to turn off state 3 first. So here it is an accepting. What is the difference between this state and this state? It is an accepting, and this is not, this time this is not an accepting because we turned it off. So okay, and we brought this diagram from the previous slide. Okay, so I hope and this is so easy, simple. It is an accepting because it can repeat itself. So for this we can write 0 static, and we can ignore to visit state 3 because we may die there. So then we can, okay, so for the time being 0 static. Let's go to the next slide. State 3, second example. So turn off state 1. Okay, second. So now we will turn off state 1 here. So it has been off. So what will happen? 0 static, then 1 0 static, and then 1, and after that this one 0 plus 1 0 static, then 1 as a whole static. Why is a whole static? Because it will repeat again itself again and again, and accepting states for state forever, always accepting state. So that is why we are putting static for it. Okay, so combine from previous slides to get, we will combine 0 static from previous slide, as the machine on previous slides it was resulting in a regular expression which was just 0 static. So this machine is equal to 0 static. This is the regular expression for this machine. We are bringing the 0 static to the next slide. Here I just append it. Okay, so this is the regular expression for this machine on this slide, and then the regular expression brought from the previous slide. So this is the regular expression. Okay, now this is the overall regular expression for which diagram? For this diagram. Okay, to acceptance state, turn off state 3. Okay, for this diagram. So let's go to the next slide. Converting a regular expression to an automata. Okay, so far we were converting automata to regular expression. Now our job has changed. You may call a reverse job. Now we will create a regular expression to an automata. But before starting this new topic, not a new topic, but I mean this is a new phase of converting it back from regular expression to automata now. So but before starting this, I want to go to the comment section. Okay. Okay, at last I'm getting some comments from students. One student is saying net problem. Okay, one student is saying that his net is not too, how should I say, the bandwidth is not too high, and he's getting this live streaming in a stacking form, so he may listen the recording later on. This is what he's saying in a local language. And I have got another comment from a student. Assalamu alaikum sir, I have little bit internet problem, almost consume internet bundle, that's why I can't play. So and I will see the lecture later. Okay, that's why I can't play. So and okay, he also want to listen the recording later on. Sir Nander Khoshala Mutki. Oh, someone is asking that today. I'm very happy. Okay, uh, let's go to our class. So okay, so I don't know why some students they are telling me in the comment that today I seem very happy. I look very happy, but I don't think so that today I'm happy. Because I'm teaching a very one of the difficult topic. So teaching compiler construction is not an easy job. Okay, so that's why I'm not happy. Okay, so we have shown we can convert an automata to a regular expression. Okay, so far I taught you how to convert an automata to a regular expression. To show equivalence, we must also go the other direction. Other direction means now we should also convert a regular expression to an automata, and convert a regular expression to an automation, okay, or automata. We can do this easiest by converting a regular expression to an epsilon NFA. What is an epsilon NFA? This is the definition of an epsilon NFA. NFA by the epsilon means transition is a finite state machine in which the transition from one state to another state is allowed without any input symbol. Empty string, yeah, empty string without any input symbol. So this is what empty NFA means. Okay, and how can we convert inductive construction and inductive construction? We will make the NFA. We will construct the NFA inductive wise. Okay, start with a simple basis. We will take a start with simple basis, and then what we will do, use that to build more, and on the basis of that we will build more and more. Okay, complex part of the NFA. What we will build more and more, we will build the complex parts of the NFA. Okay, so here I'm going to take a start. Okay, regular expression to epsilon NFA. So here is the regular expression. This means regular expression, and this is the expression. Okay, I mean regular expression, R is equal to A. Okay, so here one state to another accepting state, and we put the label or age with A. Okay, and here is epsilon empty string. So this is the way how to write an empty string which leads to an accepting state. And there is empty. So this is empty. If you are given empty in the regular expression, so this is how you can develop its NFA. Okay, so this is the basis, very simple. Now next slide, more complex regular expression. On next slide we are going to study more complex form. Here are the more complex form. Regular expression is S and then plus and then T. Okay, so this is the first start, then empty string. This here is another empty string. This is for S, this block, and this is for T, and then we are going to an accepting states with empty string. Okay, so S plus T. In case of S dot T, you can do like this. This is S dot T or ST. Okay, S, this is for S and this is for T. Okay, and the accepting state, where you will have to put the accepting state here and the block of T. Okay, and we are joining these two with empty string. Okay, you can join them as we are having dot. Here we are having plus, so you can do like this. You can do like this to input empty strings and to output empty strings from S and T to reach the accepting state. Okay, here we have asterisk. How? Oh, it seems a bit difficult for you, but asterisk. Okay, here we start with empty string, then the block S, and then we are going towards the accepting states by using the empty string or empty label. And what does this mean? This edge, okay, with empty. At the start, making or deriving a regular expression from an NFA, we may get the very first literal as empty string. Okay, so this is for empty string. Empty string. I have taught you before, while creating or deriving a regular expression, the very first literal you may get it empty. Okay, so this is empty string. Okay, empty. This is for empty string, just to reach directly the final state or the accepting state. Okay, and then empty string, and it connects with the block S, and inside S we can come from this state to this state. So with empty string you can do make some more state by and you can connect them with these states by using the empty string. Okay, so this is an automation machine for aesthetic. So these are the regular expression, and this is how we are developing the NFA for them. Regular expression, NFA for it, and then aesthetic and regular NFA for this aesthetic. Okay, let's go to the next slide. Okay, here we have to, this is a bit more complex for you guys now. Regular expression to epsilon NFA example. Okay, convert a regular expression, this is AB plus A and static as a whole, zero or more property, closure property, okay, to an NFA. Okay, so we here our job is to convert this regular expression to NFA. So this is how we are converting. We proceed in stages, starting from simple elements and working our way up. Okay, so this is A. Okay, here is the level for A to reach the accepting state. Here is B, so here is the level for B to reach this accepting state. Here is AB, so A, then empty string, then B, and then we're reaching to the accepting state. Okay, so let's go ahead. More complex for you guys. So AB plus A. Okay, so this is how we take a start, empty string, thus then we A, here A, and then B, and we are joining these two states with empty string, and then at the end it is reaching the accepting state or the final state with empty string. And for what does this part is here? Okay, what does this part mean? I mean, so we have plus A. Okay, plus A, AB, this is for AB, this part, and this for plus. So we are plussing this A with these two literals. Okay, so we are creating another state from this initial state. In other words, we are connecting this state with the initial state by using the empty string, and then we are taking this state to another state by using the label A, and then at last we are simply leading this state to the final state with the empty string. So this is how we can develop an NFA for this regular expression. Okay, another machine seems a bit more complex machine for this regular expression, AB plus A whole static. Okay, so here we take a start with empty string, then AB. So this part is for AB, and then A. This part is for A, and this static is to repeat the AB. Okay, AB, because in regular, if you will open this regular expression, so you may get AB a lot of times in multiple terms. So this is a kind of loop which brings this state to the initial, not you may call it to the initial but sub-initial state. Okay, and it will create another AB, and this label is for this whole static to reach the sorry, this part is for A, this AB, this part is for AB, and this part is for empty string to reach the final state directly. Okay, in the initial terms you may get an empty string. Okay, and the static, this is for static. Okay, this is for static. Each time it may repeat. If static, if it will come here, so either it may go on this part to create AB, or it may go to adopt this part to append A with the term AB. Okay, with term AB. So ABA, ABA, ABBA, you can create terms like this or literals like this by using this machine, or by how to say expanding, by expanding this regular expression. So this is another automata, or non-deterministic finite automata, or NFA for this regular expression. I hope so far you would have understood. It was fun to study these kind of things, and I hope it was easier for you guys. So that's all for today, and I would like to stop my lecture here, and we will start